In this animation, we're viewing a longitudinal wave or compression wave passing through a medium. And sound is a longitudinal wave, so we can just pretend this is a sinusoidal sound wave passing through the air. So you can imagine that before this wave arrived, I painted 40 evenly spaced vertical lines in the air, and then our sinusoidal compression wave arrived from the left. In other words, we started playing a constant tone from a speaker off the left side of the screen, and that sinusoidal compression wave disturbs the air molecules, causing them to oscillate left and right. And those molecules that I painted green at the beginning are just a convenient way to track the motion. Now we want to cover the essential features and vocabulary for longitudinal waves here. So I'm going to start by focusing on the direction of motion of the medium. And by the medium, I mean the air molecules. So if we highlight just one of these lines, we see that our molecules represented by that line wiggle left and right, while the wave propagates to the right. In other words, the motion of the medium is parallel to the wave velocity. And this is the defining feature of longitudinal waves. Note that this is way different than a wave on a string. In other words, a transverse wave, where the motion of a point on the string is always perpendicular to the direction of wave velocity. So watching this white line oscillate back and forth, we realize that it's simple to define the period and frequency of oscillation for this sound wave. The period is just the time for one complete cycle of an oscillating line. And the frequency is just the number of cycles per second. And these numbers are the same for every line in the animation as the wave passes through them. Next, I want to point out that one of the key properties of a sound wave is called the displacement amplitude. And that's the distance from the equilibrium position of that line, in other words, the center of its oscillations, to either extreme at the left and right ends of its motion. In other words, the double arrow in this animation has a length of twice the displacement amplitude. So for real sound waves in air, displacement amplitudes for air molecules are typically measured in nanometers. So these are very small oscillations, even when a sound is fairly loud. Now we can freeze the animation. And the next thing I want to point out is that we see regions of high density or compression propagating through the medium, and those are separated by regions of low density or rarefaction. And remembering that we're modeling the density of air molecules here, we realize that those regions of compression are going to have higher pressure, and the regions of rarefaction, they have lower pressure. So we can also define a pressure amplitude for this sound wave. And that's the difference between the highest pressure in a region of compression and the background atmospheric pressure. Or you could also say it's the difference between the background atmospheric pressure and the lowest pressure in a region of rarefaction, where the pressure is actually less than atmospheric. Finally, we define the wavelength of a sound wave. And we're going to use the Greek letter lambda for that. And that's the distance between adjacent compression peaks or the distance between adjacent rarefaction troughs. In other words, it's the distance before the wave behavior begins to repeat. In the next video, we're going to derive a formula for the wave function of a sinusoidal sound wave. In other words, a formula for the pressure as a function of position and time. And we'll also learn how to relate the pressure amplitude to the displacement amplitude. I'll post a link to that video in the upper left, and I'll see you there.